And again, y'all can see my notes?
Yes, ma'am.
Okay, well, thanks. So we're picking up basically where we left off last time. We were looking at the Riemann sum. We were taking sums of rectangles that were approximating the area between A and B for some function f of x. But now we want to look at a limit as this distance, delta x, goes to 0. And before we do that, it helps to have some rules that you probably have seen, but you may not have seen. So this way we're all on the same page. We're just going to look at some basic rules of integration, which you may have learned last semester in Calculus 1, or you may not have learned in Calculus 1. So the really basic one is any x to a power integrated is x to that power plus 1 divided by the power plus 1 plus some constant. This is a constant. That means that for the power rule, if you just have x to the first power, it just looks like x, this dx, that tells you what the variable is. This says with respect to x. So the dx stands for with respect to x, so that we know that the variable really is x. And here we've got x to the 1. So this power rule says increase the exponent by 1, divide by that new number, and always add a constant. Now let's see why that works. If we take the derivative with respect to x of x squared over 2 plus any constant. Well, since integration is the opposite of differentiation, we should get back to x. Well, what is the derivative of x squared over 2?
X.
Yeah, because we're going to take this exponent of 2, bring it out front, and we have the x. What are we going to do with the exponent on the x? What do we do with it when we take the derivative?
Lower it by 1.
That's right. So we have 2 minus 1 now, and we still have that 2 in the denominator. What is the derivative of a constant?
0.
Good. And these 2's will divide away, and we just get x to the 1, which is what we wanted. So you can see why we always have to put a constant in when we're taking the integral. Because when we take the derivative, when we go the other direction, the derivative of any constant is 0, and therefore we don't know. It may have been there. If we have the power n equals to 2, then the integral of x squared dx is x cubed over 3 plus c. The integral of x cubed will be x to the 4th over 4 plus c, and etc. Now let's do one quick thing before we continue. What if I have the integral of x dt? What is the variable this time?
T.
That's right. And in terms of t, x is just some constant. So we would just get x times the variable is t and then plus c. This is treated as a constant. And here, the value, look, we can rewrite this integral of x dt as the integral of x times t to the 0 dt. What is t to the 0?
1.
Good. So we can easily put that in if there's no t there. But now I see that this x comes out. The rule says increase the exponent by 1 and divide by that new exponent, and then add c. And therefore we do get x times t plus c. So it's very important to make sure that you notice what the integral is being taken with respect to. Is it being taken with respect to x or some other variable? So here is that example that we just did. If we're taking the integral of some constant with respect to x, that is equal to the integral of that constant times the variable to the 0 power dx. And that is equal to the constant times x to the first power over 1 plus c, which is just k times x plus c, where the x comes from the dx. That tells us what the variable will be. And so I wanted to make sure that we covered that. If we had the integral of a constant dt, that would be the constant times t plus c. The variable that there would be t. Some of these formulas we're going to use now and prove later. So one of them is the integral of the sine dx is negative cosine plus c. The integral of the cosine is sine plus c. And the integral of 1 over x is the natural log of x plus c. We're really going to use that one a lot. And the one that I left off that I forgot to put is if we have the integral of e to the x dx, what was the derivative of e to the x?
E to the x.
That's right. And so the integral is also going to be e to the x. Good. So I want you to be able to use those values. And like I said, we will prove some of them later. That was on page 1 of our notes, and I'm almost positive I sent the notes out.
Yeah, I think you did.
Okay, good. So here we are. We're going to have a precise definition of the Riemann sum. These are all the parts that we've sort of been flaky about. We have to have a partition, and that's just how many rectangles we're going to have. And you can see the partition numbers go up to n. And this is the partition of the interval from A to B, so that A must be the very first number and B must be the very last number. We're going to let delta x be the value of, be the width of our subinterval, and delta x is always b minus a over n. And we're going to let x star be any value of the function on that interval between x sub I minus 1 and x sub I. So the Riemann sum is the summation from I equals 1 to n of f of this x value that we just found times delta x, and the definition of the definite integral, the integral from a to b of f of x dx, is that Riemann sum we were just talking about, with in front of that the limit as n goes to infinity. So we're going to take the things that we've been talking about, and we're going to take the limit as n goes to infinity of that stuff. And this is important. If that limit exists, then we say that f of x is integrable. The limit might not exist, in which case f of x isn't integrable. Okay, so let's look at some examples. That definition is something we're going to use over and over and over again. So here, we want to find the integral from 0 to 5 of 2x plus 3 dx using the definition. In every single example that we do, and everything that y'all do, we are going to use the right endpoint because it's easier, and I don't think it adds a lot to your learning to move the endpoints around. So when we're looking for x star, we're going to be using the right endpoint, which is what we've done all along. So here, delta x is 5 minus 0, that's b minus a, over n, where n is just a number. So we get 5 over n for the delta x. That means that x star will be 5 over n times I. So we're going to plug this value into our function. We have f of x star. Well, that's f of 5 over n times I. And our function is 2x plus 3. So this is 2x plus 3, where x is 5 over n times I. And 2 is just a number, so I can multiply that through here. I get 10 over n times I plus 3, and that is f of x star. We already found delta x. Let's go ahead and put it here. We found that right at the beginning when we have b minus a over n. And the Riemann sum is the product of f of x star delta x as n goes from 1 to n, as I goes from 1 to n. The reason why I'm putting the i's off to the side is that I'm trying to remember in my head, what am I summing? Am I summing the n's or the i's? Here, n is a constant. It's I that changes. And that's because I is the index on the summation. So here we've got the area approximation. And that's going to be the sum, as I goes from 1 to n, of f of x star delta x Well, that's the sum as I goes from 1 to n. F of x star was 10 over ni. Plus 3. And we said that delta x was 5 over n. Are we groovy so far? Okay, swell. Now I want to multiply this 5 over n through. So 5 times 10 is 50. I get 50 over n squared, still times I, plus, and then 5 times 3.
15.
Thank you. Over n. Now, remind me now, which variable are we adding with respect to? This
I, because it's the index.
That's right. That's right. So whatever n is, it's fixed at this step. That means that I can split this into 2 parts. Let's do that in 2 steps. I can write this first term as the sum as I goes from 1 to n of 50 over n squared times I, plus the sum as I goes from 1 to n of 15 over n. There we go. What's cool about the second part is that we've just got a constant. If we're adding this constant to itself n times, then we're just going to have the constant 15 over n times n. The first term is going to use the summation of the first n integers. And we can pull out the constant 50 over n squared. So we have the sum as I goes from 1 to n of I. And tell me, what is the formula for the sum of the first n integers?
N times n plus 1 over 2.
Excellent, excellent. So we've got, I'm going to pull out that constant 50 over n squared times n plus 1 all over 2. And then we know that the second term, can I write 15 over n times n more simply?
15.
Great. So this is still my area approximation. And what I want to do at this step seems a little bit weird, but it's foreshadowing. First, I want to reduce. 50 divided by 2 is 25. So now I've got 25 times, and it 1 over n squared, is that the same as 1 over n times 1 over n?
Yes.
Okay, good. And we have that times n plus 1. What I'm going to do is move these 1 over n's. One of them will be multiplied by the n, and one of them will be multiplied by the n plus 1. And you'll see, we're going to do this because we're going to take the limit in a minute. So I'm going to write this as 1 over n times n, and then times 1 over n times n plus 1. What is 1 over n times n?
1.
Good. So this goes to 1. So we've just got 25 times. Now I'm going to multiply the 1 over n through this term. So I'm going to have n over n plus 1 over n. Is that right? if I multiply 1 over n times n, I get n over n. If I multiply 1 over n times 1, I get 1 over n. And can we simplify either of those?
N over n becomes 1.
Good. So we have 25 times 1 plus 1 over n. And that is our area approximation. But now, these pens last about 30 minutes and then they die. Now, I don't want the approximation, I want the exact value. So the exact value is called the integral from a to b x dx. That is defined to be the limit as n goes to infinity of the sum as I goes from 1 to n, x, f of x star delta x. But what's nice is that our value of this summation, we already figured out the summation, and where is the n that is left? Do we have any n's in a numerator? That's right. What's nice about the limit is n goes to infinity of 1 over n. What is nice about that?
It would make it 0, right?
That's right, exactly. That's why we multiplied through by these 1 over n's. So every n in the numerator was multiplied by a 1 over n to move the n to the denominator. So now we can take this limit easily. We have the limit as n goes to infinity of 25 times 1 plus 1 over n. And this is the integral from 0 to 5 of 2x. Was it plus 5? Plus 3. There we go. So our f of x was 2x plus 3. We still have the d of x. We had the a was 0, b was 5. And our value for the summation as I goes from 1 to n of f of x star dx is all just 25 times 1 plus 1 over n. Can we easily take our limit now? Yeah, very good. So we just get 25 times 1, which is 25. The reason why I wanted you to have the regular rules of integration at the beginning is that we can now verify the answer using the rules. So let's see. If I just look at the regular integral of 2x plus 3 dx, what is the integral of the 2x part?
Two x squared over 2.
Good. And what is the integral of the 3?
3x.
Good. And we have to put plus c. But now we're actually going to use a form of the indefinite integral that is called definite. We're going to let our x have values so that when we have 2x plus 3 dx, now we're going to take this value that we just found, x squared plus 3x plus c, and we're going to evaluate it at 5, at x equals 5, and then subtract x equals 0. So we've got 25, that's the x squared. 5 times 3 is
15.
good. Plus c minus, when x is 0, what do we get?
0.
Good. So we get 0 plus 0 plus c. And what happens with the c's?
They cancel out.
Yep. So we just get, let's see,
40.
good. So that's what we should have gotten here. 2x plus 3. Okay, let's see. Oh, we had 50. I think I changed it. No, wait, I did. Okay, that was right. Plus 15, that's what happened. Okay, good, good, good. Okay, yay. So we had a plus 15. I just started leaving off. Good. And in here also, we've got the plus 15. 15 has nothing to do with n. So it gets added to whatever value we find in the first term, and we do indeed get 40. So you can use the rules of integration to check your work. I want y'all to do this example. You can either do it on your own and text it to me, or you can do it out loud with other students in the class, and one of you can text it to me. But please talk to each other. Use your video if you need to. I'm going to go away. Are y'all working together at all?
Yes.
Okay, great.
Yeah.
Somebody let me know when y'all are finished. I still didn't hear anybody say that they wanted to do it. Oh, I see. I've got text messages. Oh, good. Y'all are communicating with one another. The Zoom recording will be posted, not just posted on our page, but embedded onto our notes page. I'll send it out, of course.
Okay, here's a station just for you.
That Siri thinks I'm talking to her. Okay. Okay. I don't know. That was Siri. So who would like to present this? Anybody? Nobody? I'll wait till somebody. Yes.
I have 6x minus 1 dx,
Yes.
and then I have 6x times dx minus 1 dx.
Yes.
And then I have 3x squared minus x. And then I have 3x squared minus x, and then the 4 and the 0. And then I have 3x times 4 squared minus 4 minus, in parentheses, 3x, 0 squared minus 0, and I have 44. Is that right?
Good.
I could be wrong.
I
Maybe
got
I'm wrong.
44 too.
Okay. So the fun thing that y'all are skipping is that this is the definition I mean for you to use. So the rules of integration are going to help you check your answer. And that's good. But we want to use this definition of the definite integral because that's what we've proved is correct. So I want you to find delta x, x star, f of x star, and then this summation. That's what it means to use the definition. So can somebody walk me through that?
Yeah, I did it that way through the sum.
Okay, good. So what did you get for delta x?
4 over n.
Good. And for x star?
4 over n times I.
Good. And f of x star?
24 over n times I minus 1.
Yeah, let's write it in 2 steps, but exactly right. 6 times 4 over ni minus 1. And that is 24 over n times I minus 1. And now we're going to put it back into this summation limit formula. So we know that the definition from 0 to 4 of 6x minus 1 dx is the limit as n goes to infinity of the summation as I goes from 1 to n of 24 over n times I minus 1 all times, what do we multiply by there?
Delta
4
X.
over n.
Good, very good. Okay, so let's move you over here. So we've got 4 times 24 is
96.
excellent. So we've got 96 over an n
N
times
squared. N
Okay.
squared.
minus 4 over n. That's it, right? And then help me evaluate the sum as I goes from 1 to n of 96 over n squared times I.
So you multiply the sum by the constant, which would be 96 over n squared.
Alrighty,
And then you use the, I don't remember what it's called, but the definition for the sum of the
integers.
integers, which would be n times n plus 1 over 2.
Excellent.
And then how you did it before, you separate 96 over n squared into, well, first you simplify by dividing 96 by 2 and getting those removed. So you have 48 over n squared.
Okay, good.
And then you split it into 48 times 1 over n times 1 over n.
Okay, excellent. And this time I moved the 48 out. It doesn't really matter, but we've got 1 over n times n, 1 over n times n plus 1. And this time I'm not going to forget the minus 4.
And then and 1 over n times n just equals to 1.
Good.
And then 1 over n times n plus 1, you get 1 plus 1 over n.
Excellent. And this 4 is not multiplied by the
No.
48. Okay, good. And now?
Now you multiply 48 by all that. So you have 48 plus 48 over n.
Well, first let's take the limit. But
Okay,
yeah,
well, then the limit, yeah, 48 will just be 48. 1 over n will be 0.
good.
And negative 4 is just 4, negative 4.
That's right. So this is going to be 48 times 1 because the 1 is the only thing left.
Yeah.
Minus 4 and 48 minus 4.
Yeah, and 44.
Good. And let's, y'all did it correctly the first, the other way. So just tell me again, using the rules of integration, we have 6x minus 1 dx. And what did you get?
44.
Well, let's do the steps. X becomes,
X squared over 2. Well, with the 6, it's 6x squared over 2
good. And then
minus
becomes
x
good.
with the 4 and 0 to be evaluated at those endpoints. 4, not 5.
Oh, 4. Thank you. Thank you very much. Okay, good. So we have 6 times 4 squared over 2. Can I reduce something there?
Just reduce it to 3 times 4.
Good. Minus 4 minus, I'm just going to put 0 because at 0, both terms are 0. 4 squared.
Oh, 16,
And 16 times 3.
48,
Excellent. 48 minus 4.
44.
So these questions are fun because you can easily verify your answer. But when I say use the definition, what I mean is use this definition because that is how we're defining this thing called the definite integral. The limit as n goes to infinity of the sum from I equals 1 to n of f of x star dx. Now, was our function integrable, the one that we just looked at? Is 6
Yes.
minus 1, and how do we know? That's right. How do we know?
Limits exist.
That's right. The limit exists. The limit doesn't go to infinity. How would we present? Oh, you would present. So Elizabeth was asking how we present. Just tell me, just the way y'all are doing now. Just tell me what to write. Okay. But wait, there's always more. We almost switched classes. That was close. Y'all almost became college algebra. I have notes everywhere. All right, let's look at example 3. We want to use the definition of the definite integral. That's the Riemann sum definition. That's the definition right here. And that's why I put a box around it, and I didn't leave it in the other definitions. So we're going to remember that's what we mean when we say use the definition. And we want to find the integral from 0 to 3 of x squared minus 2 dx. And I'm going to pretend I don't know what I'm doing. So what is A? What is B?
B is 3
Good,
and A is 0.
excellent. And that means that delta x is,
3 over n.
yeah, and I'm going to go ahead and write b minus a over n, which will be 3 over n. And what does that mean that x star will be?
3 over n times out.
Very good. So what we're plugging 3 over n times I into our function, and our function is, x squared minus 2. So let's write that. F of x is equal to x squared minus 2. So f of x star will be, let's do this in a couple of steps. How about it? We want to plug 3 over n times I into this function. So we're going to get 3n over I squared minus 2. And remind me how to square 3 over n times I?
Nine over n squared.
Good. And then it'll be also times I squared. Okay. Evangeline, are you doing all right? Evangelina, were you able to do that? Okay, good, very good. And then we have -2. Now our formula, our definition is the integral from 0 to, what was this, 0 to 3 of x squared minus 2 dx is, this is the definition. The limit as n goes to infinity of the sum as I goes from 1 to n of f of x star times delta x, where f of x star is going to be 9 over n squared times I squared minus 2, and delta x is going to be 3 over n. So we've got the limit as n goes to infinity of the sum I equals 1 to n of 9 over n squared times I squared minus 2 all times 3 over n. Are we groovy so far? Use your little thumbs up or something. Let me know. I see one. Yes, yes, yay. Oh my goodness. I'm so happy. All right, now what should we do? What's a good next step?
Multiply delta x.
Good, very good. So we get the limit as n goes to infinity of the sum I equals 1 to n of 9 times 3.
27.
Good. N squared times n,
N cubed.
and we still just have I squared, and then minus 2 times 3.
6.
Good. All right. Now, what do we usually do at this stage?
Split them apart.
Yes, that's good. And why do we do that?
Simpler math.
Go ahead, say it again.
Simpler math and to use our rules.
That's right. We want to simplify what we're taking the sum of, because then we can get back to our roots. So we have the limit as n goes to infinity, sum I goes from 1 to n. We're just going to look at the first part, 27 over n cubed times I squared minus sum I goes from 1 to n of 6 over n. And the beginning and ending parentheses encompass the whole sum. Have to grab something real quickly. Check it out. New colors. Woo. All right. So let's write down what we have here with the limit as n goes to infinity of the sum. Can I pull this 27 over n cubed in front of the sum?
Yes.
Why is that helpful?
It leaves the I squared by itself.
Good. Okay, great. And now what do we know? What is the sum of the first n squares?
0.
Squares.
N times n plus 1 times 2n plus 1
Good.
all over 6.
And that'll be multiplied by 27 over n cubed. It doesn't look like a cube. All right, and then minus, what is the sum of the first n ones?
N.
That's right, good. Make sure we've got parentheses balanced. The whole thing, we're taking the limit of the thing. Yes, question.
So wasn't it supposed to be I squared? Isn't I squared just the n plus n times n plus 1 over 2?
That's I. The sum of the first I. So the sum of the first integers is n times n plus 1 over 2. The sum of the first squares is n times n plus 1 times 2n plus 1 over 6. And the sum of the first n cubes is n times n plus 1 over 2 all squared.
Okay, so I just had the wrong formula in my head. Gotcha.
Good. All righty. Now, are we almost ready to take a limit, or do we need to do a bit more algebra?
We need to remove the n's from the numerator.
Yes, that's right. Very good. So we have the limit. And why are we bothering with that?
To be able to use limit
Right.
rules easier.
Yes, that's right. Because we've got n's in the numerator, and that's kind of problematic when we're taking n to infinity. So we've got 27 times, I've got 1 over n times the first n times 1 over n times the n plus 1, and then times 1 over n times the 2n plus 1, and it's all minus 6. Where did I get the 1 over n's? So I want to make sure everybody knows.
The n cubed.
That's right. We have 1 over n cubed, 27 over n cubed, and I wrote that as 27 times 1 over n times 1 over n times 1 over n. And each of those 1 over n's went next to a factor that I have in the numerator here. And I forgot to bring my 6 under the 27. So the 6 that was being divided is now still being divided, but it's out front. Somebody explain to me why this is helpful.
Help simplify it.
Yes, good, good. So we get the limit as n goes to infinity of, I'm going to reduce the 27 over 6. What's common?
3.
Good. So I get 9/2 times n over 1 times n.
1.
Good. And then 1 over n times n is also 1. 1 over n times 1 is 1 over n. What is 1 over n times 2n?
2.
Good. And we still have a plus 1 over n. And the whole thing is minus 6, close parentheses. Can we finally take the limit?
We still got to add everything together.
But we can't really add it together until we take the limit. Because some of the terms, once we take the limit, some of the terms will go to 0. Does that make sense?
Yes.
So what does go to 0 as n goes to infinity?
1 over n.
So now we have, without the limit, we have 9 over 2 times, I'm not going to write this 1. Is that okay?
Yes.
Let's just write it. It doesn't hurt. The second term is also a 1. The third term is a 2. and we have -6. Can we reduce that first problem? Can we make it in lowest terms?
Sorry, Ms. Moore.
Yes, what was it? Good. So we've got 9 minus 6, which is I know y'all know this.
Or-
Good. Okay, let's check it by using the integration rules. So we have 0 to 3 of x squared minus 6 dx. Is that right?
Yes.
Okay, thanks. And x squared will become,
Or it was -2, it was -2, x squared -2.
thank you. That'll make a difference. Okay, so x squared becomes, what is the integral of x squared dx?
Three x cubed.
It's x cubed over 3. Good, and what is the integral of 2 dx?
Two X.
And we're evaluating this between 0 and 3. So when x is 3, we'll have 27 over 3 minus 2 times 3 is 6. What do we get when x is 0?
0.
And 27 divided by 3 is,
9.
and minus 6 is,
3.
and we're happy. We got the same thing. So I want y'all to do all of that stuff. And just by the way, all of these steps are in the notes. All the stuff that I've been scribbling are neatly in the notes. I want y'all to do all of that stuff from 0 to 3 of 4x squared minus 1 dx. So when I say use the definition, what do I mean?
The sum.
That's right, use the Riemann sum. I think I'll just put that from now on. Use the Riemann sum definition. That'll be clearer. Okay, but as before, I'm going to shut up. I'm not really going to go away, but I'm going to be quiet. So you won't see me. I just realized that class is almost over. Okay, so what we're gonna do in class on Wednesday is pick up here. So somebody is gonna present this at the beginning of class on Wednesday. And you will be able to do the first 3 problems in assignment 3. Assignment 3 is listed at the end of the notes from today. You will be able to do questions 1, 2, and 3. I'll send that out as well, but I want to make everybody sure. I want to make sure everybody knows that we can do 1 through 3 on the assignment. Are we good?
Yes.
Thank you for bearing with me. I really apologize, and I promise this is not a normal thing. I couldn't get to school today, so we would have otherwise had a no show, but this is better. Homework answers. So the reason why I'm not posting the homework answers is that I want you to find them using the regular rules of integration. So using the rules of integration, you'll be able to check your work. Okay, and if there are any questions about that, just text me. Oh,
I was gonna ask.
pardon?
Oh, no, I was gonna ask for assignment 2. Did you want us just bring that on Wednesday also?
Yes, I would really appreciate that. Actually, for the homework, you do 1, 2, and 4. 3 we have to wait. 3 is a proof. So what you're gonna do 1, 2, and 4 from assignment 3. For homework. Oh, and anybody who's watching this video later, please just upload or send to me the what you got from doing example 2. All right, yay. Have a wonderful day, everyone. I'll see you in real person on Wednesday.
Bye.
Thank you. Have a good one.
Bye.